What is coagulation? I already asked you, since we're working on the videos, I know this, the question in the first lecture, what is coagulation? And one of you answered it. What is coagulation? Yeah? Mm-hmm. So here we understand how particles stick together. And coagulation is the theory describing how the number of particles decreases over time because they stick together. So if we have now a lot of particles and they move and they hit each other, they stick together, they form a new, we will take a look at this, and describing this over time, so the development of particle number over time, this is the theory for coagulation. In this lecture, we will keep it very simple, monodisperse system, and we only will look at Smrokholski coagulation, named after the guy who gave the theory. And I think for, one important thing is you will get the second homework today. So there you also have to calculate something. Again, you will have 1 week time. And one thing which I really like to say is, please name okay. It's outside, but I'm now, I want to know what they are watching. Yeah, please be aware with naming the documents correctly. So there's only one way to name them correctly. And this, I mean, a few of you lost points because they named it completely randomly. But I was also quite nice. The thing is that it takes a lot of time for me to figure out which document is to whom when you don't name it correctly. It's a professional official document. It's very clearly in the task what you have to do. Just do it. It takes for me a lot. It saves a lot of time for me. Okay, that's the reason why. Because if not, if you name it correctly, I have the list with your email and I have the list with your homework and I just can do it like this. If not, I have to go in each individual homework and say, okay, where's he and where's the homework? And so please help me with this. And then we're done with the 2 homeworks and you already have 20%. Some of you already did the seminar, so have already done 40%. Okay. So for today, I want you that you understand what is coagulation, the same as you understood now, hopefully, what is adhesion. We'll need this board later. And of course, I would like to talk about some applications of coagulation theory. And the last thing is that we will come with a model again and we will make use of diffusion. And this is the relation to particle movement. And this is also to highlight, and this is, I mean, I told you very often, movement is very important for describing aerosol behavior. But what is also very important in movement is, because it pops up all the time, what is extremely important in movement of nanoparticles? If you look on the slide. Yeah? Size, yeah. But which effect? So we have Navier-Stokes, but one of them always pops up again, when we talk about fibers, when we talk about. Now here it's again important. Basically we just develop the model more and more. Right, diffusion is extremely important. And diffusion has to do something with coagulation. So one application we already had is gas sensors. And gas sensors, and this is from a flame process. A flame process is an extremely cool process. We had it in the first lecture, right? So for carbon black. And basically you have a liquid precursor, and then you spray the liquid precursor through a nozzle, you get droplets, and these droplets are burned. And when they burn, you crack the molecules and they will react. And in this case, you can form any kind of oxides. And what you see here is the particles grow and then they stick together and they stick more and more and more together. Here we have thermophoretic deposition. And this sticking here is based on adhesion, but basically what we have here is coagulation. Okay, the particles grow in the flame, and at one point they just don't grow anymore. They are outside the flame, they are cold, they are not liquid anymore, but they meet each other. And when they stick, they coagulate. These sensors are extremely cool. Just to give you, to finish this, these flame processes are extremely good for industry because the efficiency is extremely high and you have a very high output. Okay, so you can make a lot of sensors, materials, whatever with the flame. You don't have much waste. That's also a very nice thing. And at the end, you have these sensors here. They're extremely small. And this is the performance of the sensor. And in this case, it's a sensor which should detect formaldehyde. And formaldehyde is something if you have, for example, cancer. The amount of molecules in your breath changes. And the sensor can detect it, but the sensor has to be extremely sensitive because the amount of change is significant but quite low. And these sensors from the flame process are so good because they have this extremely high porosity, up to 98%. And this means you have a huge area, right? High porosity, very small particles, and this huge area gives the molecules the chance to hit the area. And what you do is you measure conductivity. And the conductivity changes. And this is what you see here. So you have a sensor, and the sensor has a certain resistance or conductivity. And then you apply formaldehyde, and the amount is 10 parts per billion. So this is the change we are talking about. Here, 10 ppb of formaldehyde, and you see the sensor significantly reacts to it. And this is much more sensitive than you would need in breath. And the nice thing is that after a few minutes, you just go to normal air, and the sensor goes back to his old value. Then you go to 5 ppb, 3 ppb, so 3 parts per billion can be detected by the sensor, which is extremely good. However, the problem we have is that in our breath, we not only have formaldehyde, we have also other things. And these other things will also be detected by the sensor. And this means your sensor reacts. And it does not have to be only sensitive, it has to be selective. It should only react to formaldehyde, but it does not. So your sensor gives a signal, and then you don't know, is this formaldehyde or is this NH3? They are very close to each other. Or in the other case, it's ethanol and formaldehyde. And if your mobile phone tells you you have cancer, you want to be very sure that it works, right? And in this case, you can be very happy because it should detect it on a very early stage, and then your chances are extremely high to get a good cure. So what do you see here for these 4 types of sensors? What do you see on the x-axis? Yeah? Yeah. So all of them are tin oxide, SNO2, right? All of them are tin oxide, and this is basically what is sprayed here, tin oxide. But all of them have a doping. So a small amount, and in a flame it's very easy. You just mix the chemistry and then you get doped materials. PT, SE, PD, and TI. And what you can do is, if you know all 4 materials, you can put all 4 into your sensor, you make a little bit of statistic, and then the sensor for sure tells you, okay, the amount of formaldehyde is too high. So one material is not selective enough, but the combination of different materials, they give the selectivity into the sensor. And in this case, you can make really, really nice gas sensors by these flame processes, extremely cheap, extremely sensitive, extremely selective, and that's quite nice. And the formation of the film here has a lot to do with coagulation. Another thing is fluidization. We talked about it. So in fluidization, we have our nanoparticles, and they stick together, right? Adhesion. But what's quite interesting is what happens in the fluidized bed. So what happens here, where you see this millimeter flying around. And at this time, and this is also what I investigate, I say that the size of the agglomerate is not static. And all the time, the agglomerates, they coagulate because they meet some other people and then they grow. But also there is stress from the fluid and from the impact, so they also detach. And we have one publication, and I think it's the only publication investigating this, that's quite weird, where we showed that the size of the agglomerates over time changes, and also the porosity over time changes. Yeah? Yeah, that's a very, very nice intro to this slide. So, and this is something for my class is extremely important, and in the literature, it's always different. So in my class, and this is because I come from these flame processes, is a primary particle, is a single particle, a single spherical particle, something like this or like this. And 1 second. When you're in the flame, or in the area of the flame, somewhere here, these primary particles, they grow just to nucleation and then also condensation, and they grow. And at this case, they are liquid because the temperature is 2000 degrees, or something like this. So what happens is we have an area in the flame where we have these primary particles. But they move very fast, and this means they can also touch each other. And this is already coagulation. And then we have coagulation with coalescence. And this is what you see when you're in a train. And it's raining, then you see water droplets, and when one water droplet catches another one, they coalesce. So they just form a new droplet, right? So this could happen here when they are very liquid, very hot, and they meet and they just form a larger droplet. But what could be also the case is that when we are a little bit more above, or the temperature within the liquid, the primary particle already solidifies, it will not completely merge. And then we will have these particles and they coagulate because they meet each other, but they don't completely coalesce, so they don't form a droplet. So what they form now is aggregates. And aggregates means these primary particles are still distinguishable, as you see it in this image here, right? So these one, if they would coalesce to a new one, the droplet would be a larger droplet. But here we don't have a larger droplet. We see each single individual primary, but it's somehow connected to the other one. And this is due to solid sintering. So in aggregates, we have covalent bonds. And since this one here goes more up in the flame, the temperature rises and the aggregates completely solidify. And when the aggregates solidify, they don't form any chemical bonds when they meet. So this means we have another aggregate here, and this one, and they form an agglomerate. And the connection in the agglomerate is due to physical forces, adhesion force. So primaries are the smallest entity. And primary particles here, you can see them in the TEM picture, right? So these very single, you could put a sphere on each of them. Not perfectly, but with a very, very good approximation. So here, this is an aggregate, and you see the primary particles in them. And when primary particles are connected by a solid chemical bond, this is an aggregate. And when these aggregates, and it's normally not the primaries, it's the aggregates, because you don't find from a flame a lot of single primaries. And when these primary aggregates meet each other, and this is what I try to highlight with a red line, we have agglomerates. And the agglomerates, this is what you saw in the fluidized bed flying around. Or the film of the sensor is a big agglomerate, right? Aggregates which are sticking together due to adhesion. This is my definition. It's not, in the literature, you find mostly not a definition which is this sensitive, because mostly the term aggregate and agglomerates are vice versa. Aggregation could be the same as agglomeration, or mostly. But here it's important to distinguish, because I want you to understand how these agglomerates are built up. And they are built up because aggregates adhere due to physical forces, and the aggregates themselves are chemically bond primary particles. And the process of aggregation or agglomeration, this is coagulation, because this is particle meet, the number of particles decreases, because if three primaries form one aggregate, three particles are now one particle. Okay? So the number decreases, and this is coagulation, decreasing of number over time. And when 3 or 4 aggregates meet and make an agglomerate, the number of particles decreases. So it's coagulation again, but the physics is a little bit different. Do you have the feeling you have understood what I told you? Or are you confused? No, like I don't understood it, or It's okay. It's okay? No, it's not okay? It's okay? Yeah? Okay, good. I will put it in the homework. I think with the slide, it's a nice part in the homework, and it's something, yeah, I have to watch a little bit on the time, but this is really crucial for me, but this is, it's not complicated. You just have to write it down 1 or 2 times, and then you should be able, with the slide, to connect it. Good. So basically, coagulation, as I told, is, and now you see already here aggregation, and this is from an old paper. They don't distinguish if aggregation or agglomeration here, so please be careful. And basically, the question in coagulation is, how do we get the golden one? Could be an aggregate, could be an agglomerate here. And basically, there is an equation. This is the equation you have to solve. It's a population balance. And the equation is a big equation, but the effects in the equation are quite simple. So how do you get the golden guy? The golden guy you can get by birth by aggregation or agglomeration. I would like coagulation here, but okay, it is as it is. So it means this one and this one, these two, they meet. They collide, and they aggregate or agglomerate, depending where in the flame we are. And by this, we get the golden one. So this is one part we have in the equation. But we also have death by aggregation. And death by aggregation is the blue one. And this means that this one meets another one. So we have the golden now, but he meets this one, and they stick together. So now we have this big guy here. So we already lose a golden one. Then we have death by fragmentation. And death by fragmentation is this one, and this means we have our aggregate or agglomerate, and there is force applying on it, and it breaks away. And this is what, in my opinion, happens in a fluidized bed, for example. So this means the golden one, again, is gone and goes into this and this. But we also can have birth by fragmentation, and this means it could be we have, again, the bigger one, and the bigger one breaks away, and now a golden one appears from the bigger one. So we have 4 possible outcomes to get the golden or get rid of the golden, and this is birth by aggregation, death by aggregation, death by fragmentation, or birth by fragmentation. And therefore, I would now come to an equation how to describe the number of golden particles for the most simple case. And the most simple case is coagulation of monodisperse spheres. So it means our primaries have all the same size and all of them are spheres. And now we have to think, okay, the particles, they have to move because they have to meet somehow, right? And you know already the movement of nanoparticles is not very simple. We would need the Navier-Stokes equation to describe how these two move. But again, we can make a lot of simplifications. And the simplest case is if we just look at 2 nanoparticles, and there is not much happening to them, we just consider diffusion. There is no wind, there's no electrostatic or whatever, no external force, gravity we don't need, they are too small. We don't consider the drag to don't make it too complicated. So we just say, okay, we look at diffusion. And this is the Smocholski coagulation. So also here or in the flame, we can say, okay, they just meet because of diffusion. In the flame, we also have convection, so it's already questionable. And now we have to think, okay, when do they meet? And to do it, or to calculate it, we make some simplification. And one simplification is, so this is dp, the diameter, this has the same diameter. And the first one, I say, okay, this one doesn't move. This is fixed. Why? Because if one doesn't move, it's much simpler to describe. And at the end, it doesn't matter if both move or this one is fixed and only this one is moving, because movement between particles is relatively, right? So it's the same with drag. For drag, it doesn't matter if the particle moves through a liquid or the liquid moves around the particle. At the end, it's the same. The relative velocity is the important case. And here it's the same. And another simplification we make is that we say we don't consider this one as a sphere. We consider it as a point. Then it's much easier to calculate. And if we consider it as a point, we lose the size, right? But we only need the size as a question, when do these two move? And they have the same size. So what can I do with my left particle when I say I decrease this to a small point? What can I do with the left one, with the fixed one? Yeah? Yeah, I take it as a reference, but I have to do something with it. It's correct? Yeah, but I have to do something with it. I'm not sure if I get your point. What do I have to change? So I take this one and I decrease the size here. What do I have to do with the left one to relatively don't change my system? Yeah? No, because if I consider it as a point, the chance that they meet changes. So if I have two spheres and there's a chance that they meet by diffusion, right? And so now I decrease this one, the chance changes. But I want to describe the system, so what do I have to do? Yeah, exactly. So I just have to double the diameter. And this is my new diameter, and this is 2dp. Why? Because now it doesn't matter if this white bead or if this blue one would hit this distance. It would describe that they are touching each other. So now I have to figure out how this one moves, right? So and therefore I can use the flux. The flux, its fixed first law, is diffusion coefficient. dn dx. X is basically here, my area. Not area, it's not time, it's space variable, okay? So where I'm in my coordinate, in the room. N is the number concentration. So the number concentration of these ones going here. And this depends on the diffusion coefficient, and basically then I have an expression of the number concentration on my coordinate. And this is the, no, that's fine. So from here, I would like to describe the rate of collision. So this is the number concentration of particles. How many particles do I have? And this is the question, how many collisions I have. They are connected, but they are not the same. The number of particles in coagulation decreases. And the number of collision decreases or not? Yeah, also decreases, right? The less particles I have, the less collisions I will have. So what is what is the rate of collision? The rate of collision is dn dt. So small n is collision, large N is number concentration. So here we have N is number concentration. And this is the flux times the area. The flux tells us how many particles just going, right? The flux through an area. And now I need the whole area, and then I can count my collisions, right? So if I know how many come and how large my area is, I can count the collisions. And this is then 2, I want to have it like here. Minus pi 2 dp square, that's the area, and then it's the, that's what I'm missing, dn dx. So this is just the area, and here is the flux and the minus. I'm sorry, I forgot, but you know it probably from Fick's law. So this equation was solved by a guy called Fuchs, I think 1960, 50 or somehow. He's a very important guy in aerosol science, and he gave a solution for this. And the solution he figured out to express dn dx is dn divided by dx is minus 2n dp. And now I can make use of it. Now I know dn dx. I can put it in here. And if I put it in here, I can say dn over dt is 8 pi dp dn. And this is for one selected particle. So we only look at this one here. How many collisions arise for this particle here? But if I want to go to multiple particles, something changes. And this is dn dt. And now I have n half 8 pi dp dn. So I add n half. Why? So this is for one particle. And this is for all particles. So what I consider now is not only this one, now I take a box with thousands of particles. And for all of these thousands of particles, I want to calculate the number of collisions. Why the number half? Why not just the number? Yeah? Yeah, very, very good. So basically, I would apply this model for all my particles, right? So if I have 1,000 particles, I would 1,000 times apply this model. And this means exactly as you said, if I have particle A and particle B, and then I have particle B and particle A, they only hit once. But I would count it twice. So this is why I have to halve it. So if I count the collisions, I need to be sure that I don't count the collision double. And this is 4 pi dp d. So then we can say the rate of collision numerically equals the number concentration but opposite sign. 4 pi dp dn. Here's something missing. What is missing here? N and yeah, very good. N and the dependency is? Yeah, very good. Thank you. Exactly. So n squared is missing. Thank you. So here this is n squared. And this is both are simple equations, right? So if you think where we're coming from, this is something we could calculate. And this part here is a constant, and this is K0. And K0 is the coagulation constant. So if you know the coagulation constant, and the coagulation constant depends on two things. It depends on diffusion and on particle size. And basically, with equating drag, and if you look in Einstein's paper, you could show that even the particle size canceled out. And this means that the coagulation at the end only depends on the diffusivity, right? That makes sense. If they diffuse very fast, they meet faster. And the number. So how fast a system with a lot of particles coagulate basically depends on the number of particles. That's it.
I wonder how on the third line the small n became the large n, a n dt.
From here to here, it's because the number of particles, the concentration and the number of collisions, they are numerically the same. Okay, so if you have 1,000 particles, you have a certain amount of collisions, and you have a certain amount of particles arising from this collision, and this is basically the same, only the yeah, very, very good. The rate of, just to briefly summarize, the rate of decreasing collision is the same as the rate of decreasing numbers. So, what can I do now with my nice equation here? What can I do with this equation? So now it's dn dt equals k0 n squared. Yeah? What kind of equation is it? Yeah. We can separate the variables. So we have dn n squared equals k0 dt. Sorry. Minus. And then we integrate dn over, n squared, and we integrate what are my integration borders? Or don't I have integration borders? What are the borders of the integral? For time, for example, what are the borders for my time? Yeah? Yeah, and what would it be probably?
They are continuously colliding, but we are considering for a certain period.
Exactly, we consider a certain period, and if we consider a certain period, when does it start?
0.
Yeah, and where does it end? Yeah, so from 0 to t, so this is quite simple. How is it here? Huh? Yeah, so it's from, I'd call it different. I have it from n at t, right? There is a number, and we have a starting concentration n0. And this goes okay, so this is basically, and this is what I stated at the beginning, I said coagulation is the theory to describe the change of numbers over time due to coagulation. And this is the number of particles at a given time. And to describe this, we just need the starting number, the time we're looking at it, and the coagulation coefficient or constant, which is something you find in the book, you can measure, you get from literature. And this is the most simple case. This is for monodisperse spheres. So for monodisperse spheres, we can put them in a room, and if they coagulate, we can tell if we start with 1 million, after which time do we get which amount of particles. So here it's in the slides, right? So this is the equation, initial number of particles, coagulation coefficient, and here you see how it behaves. And this is something probably not very surprisingly. It is extremely fast at the beginning, and then it cancels out. And if we go back to my brother-in-law, we see this picture, and now you imagine somebody in a room smoking. And all of you know that the dust, the haze, right, decreases very fast. So we see the smoke at the beginning, but it takes not much time that it kind of dilutes. And this has to do also with coagulation, right? So with this behavior here. Because the number of particles decreases very, very fast. So also here again on this picture, you can see something related to coagulation. And this is that if somebody smokes, you see the smoke, and very fast you see a change in reflection, in haze, and these things. And this is, again, I hope something new you discovered. Good. What also changes is the size of particles. And the size of particles can be given from a mass balance. And the mass balance is extremely simple because we say that the particle coagulate, so the number change, but the mass does not change. We don't lose any particles in terms of mass. So the mass for the particle at the beginning, so we have 1 million particles with 10 nanometer, and after a while we will have less particles, but with a larger size because they coagulate. So we can set the balance, and then you just can rearrange the equation. And if you rearrange the equation, you can make a statement for the diameter at a given time. So after 10 seconds, after 20 seconds, after 20 minutes, whatever. And what is important here is that if you look at this equation, the particle size increases with the inverse cube root of number concentration. So this means an 8-fold reduction in number doubles the size. So if you have a certain size and you want to double the size due to coagulation, you need to reduce the number of flying around particles by 8. And this is a quite nice finding. And now I would like to show you some applications, and then we are done for today. So the applications is here. Very nice application. So this is BioNTech. I took it from YouTube, and I really like it because it's from 2016. And 2016, they made this nice talk about their technology, and they want to get some investors, so they talk about their technology. Then on one of the slides, you find a sentence, a point. They even don't say it. They say, our technology would work in the case of a pandemic. We could deliver very fast mRNA vaccinations. And at this time, I don't know, 2,000 people watched the video, so nobody really takes care about it. And then a few years later, you know what happens. But what is important is also the relation to this class here. And this is how they do the vaccination. So you have the RNA, and we cannot talk about RNA here. That's not our field. But once you have the RNA, what do you have to do with it? What do you have to do with the RNA? Yeah? Yeah, but this is not what we're looking here. Here we're looking about nanoparticles and so on. It's correct what you're saying, but I assume, okay, we have some smart people and they delivered the RNA. And in Bionic case, it was quite fast to have the RNA. But what is, for us, the interesting part then? What do you have to do with the RNA that you can use it as a vaccination? Yeah?
Like we just generalize, we just give them a foreign particle, we just see that how they react with them and get to know that like how faster they are.
Yeah. Very good. So the thing is, the RNA is not stable. If you just put the RNA in the body, you destroy it, that's it. So you need to save it. And to save it, you make something around, you make a nanoparticle around, a lipid nanoparticle. And the size of the lipid nanoparticle governs where it goes. We had this when we talked about sizes, right? So, and if you take a look here, it's a lot of particle technology in here. So because you need all the physiochemistry, you have your lipid carrier, which goes around, and you have the physiochemistry, which is like size, surface charge, and so on. And these are the criteria for the lipid nanoparticles. And what's extremely, I want to buy it, I don't have it yet. In the Deutsche Museum, they have now the first reactor BioNTech used for the first million of official vaccinations. So this is where they made this encapsulation step. Make a guess how large the reactor is. The first million of vaccinations. How large do you, it's now in the German Museum of Science. Yeah? That's the size. That's normal lab equipment they used for the first million. Right? So we're talking about nanoparticles. Think about the nanobiome. The first million of vaccination was done in a lab reactor. Like if you go in Thomas Schupp's lab, he has, I don't know, 50 of them. And this is what they used for the first 1 million. And there you just need to play around with the chemistry to get the perfect size of your nanoparticle. Another thing, and this is why I pointed up here, is this one. And this is actually, when I found it, I applied for a position there, but they never, because they had a position open to this, but they never invited me. So you have to do the left one, and you have to scale up. And this reactor is not perfect. I mean, the 1 million was somehow feasible, but it's not how we do, right? You know, from the labs, you can do a lot of things in these kind of reactors, but if you go in industry, they don't use these kind of reactors. So they thought, okay, how can we scale up? And one idea to scale up is using a nanoassembler, which is basically, and this is also what you saw in the second lecture, is nanochannels. And in the nanochannels, you see here, at large manufacture volumes, clogging aggregation was observed. So basically, all what we have here and what we have here is a problem in their system, because the lipid particles, they coagulate, the number decreases, but the size increases, and at one point you get clogging of your system, and you want to adjust everything that you have control over this behavior. And for lipid nanoparticles, this is not a bad assumption. Okay. Good. I think we're done here. To sum up, I hope we could today finish adhesion, and I really hope you understand the model we are using in adhesion. And then we talked about coagulation. I hope you understood the relation from coagulation and adhesion, what is different, what is common, how they are connect with each other. What is coagulation? How do we describe coagulation in the simplest case? So I really want you to be able to explain this model and give these kind of equation. It's quite simple math, so it's something you could learn. In the homework, you have to calculate with this also. There is a small example, and if you don't have any questions, we're done for today. And then we will have in half an hour the seminar. Yeah? Any questions? Okay, then see you in half an hour.